I want you to imagine, just for a second, hiring this brilliant new assistant.
Okay.
I mean, someone who learns incredibly fast. On day one, you sit them down, you teach them how to handle your incredibly complex scheduling.
And the really tedious stuff.
Yeah, exactly. And by the end of the day, they have completely mastered it. It's flawless.
Sounds like a dream employee.
It does. But then, on day two, you teach them a new task, like how to file your monthly expense reports. And they master that too.
Great.
But suddenly, you look over and this brilliant assistant they've completely forgotten how to tie their own shoes.
Oh, wow.
Or like how to send a basic one-line email.
Right. It is a completely jarring image. You'd assume if they learn the expenses on Tuesday, they still know how to send an email on Wednesday.
Exactly. And that exact paradox is causing a pretty massive hidden crisis in the AI industry right now. We are looking at a fascinating new paper from the University of Illinois Urbana-Champaign.
Yeah, UIUC.
Right, and it's titled, Do Self-Evolving Agents Forget? We're basically going to explore this undocumented problem of what the researchers call capability erosion in self-evolving agents.
It's a huge issue.
It really is. And of course, we're going to unpack the researchers' proposed fix to help these systems retain your past knowledge while continuing to evolve.
Right.
So, okay, let's unpack this because the entire tech industry has essentially been operating under a massive, completely untested assumption.
Yeah. The holy grail of the industry right now is creating what we call self-evolving entities.
Right.
And we are not just talking about standard chatbots here.
No.
We are talking about autonomous agents, AI that is given a complex goal and just left alone to click buttons, browse the web, evaluate its own failures,
And just autonomously rewrite its own rules.
Exactly, to get better over its entire lifetime without any human intervention whatsoever.
It sounds like, the ultimate employee. It just compounds its own intelligence every single day.
That is the dream. But that dream rests on a really flawed assumption that this continuous evolution is monotonic.
Monotonic.
Yeah, in the context of learning systems, monotonic essentially means the capability graph only goes in one direction, which is up.
Right, so it never dips.
Right. The assumption is that the agent only accumulates capability. It retains all its foundational skills while seamlessly, bolting on new ones.
But this paper from UIUC, it proves that monotonic growth in these unconstrained agents is just an illusion.
Yeah. What's fascinating here is that they found the exact opposite is happening.
Wow.
As an autonomous agent shifts its focus from an old task distribution, let's call it task X, to a highly complex new task distribution like task Y, it actually suffers from severe capability erosion.
Really?
Yeah, the repeated self-updates it makes to master task Y actively weaken and in some cases destroy the internal structures that supported task X.
So it's basically a zero-sum game of brain space. To put it in human terms, it is like studying intensely for a French exam all week. You do incredibly well in the exam, but then you walk out and realize you've accidentally overwritten your ability to speak Spanish.
Yes.
The adaptation to the new task creates destructive interference with the old one.
That destructive interference is the absolute core of the problem. And it is vital to understand that this isn't just a single drop in a test score.
Right.
The researchers actually break down this erosion into three very specific modes of structural forgetting.
Okay, let's go through those.
Sure. So the first mode is the most straightforward, which they call retrospective capability decay.
That is the literal drop in performance on previously mastered tasks, right?
Exactly.
Like the agent masters the basic stuff, spends a week learning complex new edge cases, and suddenly its success rate on the basics it falls off a cliff.
Yes. The basic competency just evaporates. But the second mode of forgetting is where the agent's behavior gets genuinely bizarre. The researchers call this behavioral policy drift. As the agent continuously updates itself to handle extremely difficult, complex tasks, its underlying workflows become bloated.
Bloated how?
It starts adding highly unnecessary, convoluted steps to really simple tasks.
Now, hold on a second. I need to push back on this being a bad thing.
Okay, sure.
Because if an AI agent is handling, say, my corporate finances or my supply chain, I want it to be over-defensive.
Right, you want it to be careful.
Yeah. If it learns to add validation checks and multiple verification steps because it encountered a complex edge case, shouldn't we view that added caution as a feature, not a bug?
I mean, added caution is great, but that is not what is happening here.
Oh, really?
No. The agent isn't just double-checking its math. Unconstrained, the AI repeatedly rewards itself for creating highly specific local repairs for difficult tasks.
Okay, give me an example.
Sure. So if a highly complex airline booking task fails, the agent writes this massive error recovery loop into its core workflow.
Makes sense for an airline.
Right. But then when you ask that same agent to do a simple task, like just checking a retail price, it applies that same massive airline error recovery loop.
Oh, I see. So it's applying maximum complexity to minimum effort tasks.
Exactly. And that introduces catastrophic noise. The bloated workflow basically becomes paralyzed.
It just freezes up.
Yeah, it starts rejecting perfectly valid actions, or it gets stuck in these endless conservative fallbacks for absolutely no reason.
Blah.
It is like a company instituting a mandatory 10-step, multi-departmental approval process just to buy a single box of paper clips.
You will never actually get the paper clips.
Never. The simple task entirely fails because the workflow has drifted so incredibly far from its original compact logic.
So the agent basically bureaucratic tapes itself into a corner.
That's a great way to put it.
Okay, so we have basic decay, we have this bloated policy drift. What is the third mode?
The third is generalization erosion. As the AI adapts to the new complex environment, it becomes hyper-specialized.
Meaning it loses the big picture.
Literally, yes. It narrows its effective reasoning space, overriding its broad, general problem-solving skills with highly specific, narrow responses tailored only to the new environment.
So if the AI is rewriting its own rulebook, that explains the paralyzed, bloated workflows.
Yeah.
But what happens when we look at the actual tools and memory it's using to execute those rules?
Right. That's where we get to the architecture.
Exactly. That brings us to where this erosion is actually taking place. The researchers identified 4 distinct dimensions, or repositories, I guess, where these AI agents evolve. And the damage happens in all of them.
It really does.
Let's look at the first dimension, workflow evolution.
Workflow evolution is exactly what we just discussed with the paper clips. The agent modifies its executable policy graph, its core operating logic.
And they tested this on a specific framework, right?
Yeah, they used an agent framework called Evo Agent X running on the Tatu bench. They started the agent on basic, simple tasks and then forced it to master highly complex domains like dynamic airline booking or retail domains.
And the simple task success just plummeted.
Totally tanked.
The AI tried to apply complex routing validation logic to basic, everyday queries, and it just choked. So the core rulebook gets corrupted.
Right.
The second dimension they tested is skill or tool evolution. This is where the AI modifies a bounded repository of reusable procedural tools.
The key word there is bounded. In their testing with the MEM skill framework on the math benchmark, the agent was given a physical capacity limit of exactly 30 skills.
30 skills.
Right. Think of them as discrete software tools the agent can pull out and use to solve a problem.
I picture this like an adventurer's backpack.
Okay, I like that.
You only have 30 slots in the backpack. When the AI is learning general geometry, it synthesizes some great geometry tools and puts them in the backpack.
Yep.
But then the environment shifts, and you tell the agent to master complex number theory. It starts inventing all these shiny new number theory tools, and to fit them in the backpack, it physically has to reach in, grab the general geometry tools it previously relied on, and just throw them away.
That is exactly what happens. The newly synthesized specialized tools progressively dominate the limited capacity of the repository.
So it just tosses the basics out.
Pretty much. The historically useful skills are deemed underutilized in the current moment, so they are mercilessly evicted. The system quite literally deletes its foundational knowledge to make room for the new specialization.
Which brings us to the third dimension, which feels even more fundamental to me.
Yeah.
Model evolution.
Yes.
This is where the AI is physically changing its actual trainable parameters. It's not just swapping out tools in a backpack, it is rewiring its own brain.
They put this to the test using an AI framework called STAR on the MedMCQA dataset.
That's a massive database of medical questions, right?
Yeah, exactly. And they tested this on models like Quen 3.0.6b and Llama 3.23b.
Okay, heavy hitters?
Right.
Yeah.
They started the agent on a curriculum of human anatomy. Once it mastered anatomy, they shifted the curriculum, moved through biochemistry, and forced the agent to specialize in dental medicine.
And as it learned the dental stuff, its scores in basic anatomy plummeted.
It suffered classic catastrophic forgetting.
Because the physical capacity of the neural network's parameters was co-opted.
Exactly. The later stage updates continually adapted the model toward the newly encountered dental domain. But in doing so, they physically overwrote the parameter regions, the neural pathways that previously supported the earlier anatomy reasoning.
That's wild.
Yeah, the pathways that once triggered a correct anatomy answer were rewired to trigger a dentistry answer.
The implications of that for a real-world medical diagnostic agent are terrifying.
Absolutely.
You don't want an AI forgetting baseline human anatomy because it spent 3 weeks specializing in, like, jaw structure.
No, definitely not.
And finally, we have the fourth dimension, memory evolution. This isn't the physical brain wiring. This is the AI updating an external retrieved memory store. Like, the researchers called it a dynamic cheat sheet.
Right. This agent continually updates this external cheat sheet using self-verified successful experiences.
Okay.
But just like the 30-slot backpack, unconstrained memory updates create intense retrieval competition.
Because it just gets too crowded.
Exactly. As new, highly specific memories accumulate from the complex tasks, they bury the older foundational memories.
So even if the foundational memories are still technically in the database, the agent just can't find them anymore.
The sheer volume of new information suppresses the old information. The old task retention degrades severely, even if the underlying model weights haven't changed at all.
It is a pretty bleak picture. Whether we look at the overarching workflow, the backpack of skills, the physical neural pathways, or the external memories, the agent is just leaving a trail of destruction behind it as it learns.
It really is.
So we have the diagnosis. How do we treat it? Since this erosion happens across all 4 dimensions due to this destructive interference, how do we stop it without just, freezing the AI and preventing it from learning anything new?
That is the million-dollar question for the future of artificial intelligence. To solve this, the UIUC researchers propose a unified framework called Capability Preserving Evolution, or CPE.
Okay, CP.
The core mechanism across the board is the introduction of a retention regularizer.
A retention regularizer. Break down how that actually functions for us.
The goal of CPE is not to halt the evolution. The goal is to bias the agent's evolution toward what the researchers call low interference solutions.
Low interference.
Right. So the mandate becomes, yes, optimize yourself to master the new task Y, but you must do so in ways that minimally disrupt the structures needed for the old task X. CPE mathematically constrains the destructive drift we've been talking about.
Let's look at how this retention regularizer actually works in practice, going back through those 4 dimensions.
Yeah.
Starting with workflow evolution, the bloated rulebook. How does CPE stop the agent from inventing a 10-step paperclip approval process?
In the workflow dimension, CPE injects what they call anchor behavioral signatures.
Anchor signatures.
Yeah. These are core objectives, output constraints, and critical failure avoidance behaviors extracted directly from the original successful simple task workflow.
So it's like a guardrail.
It essentially builds a boundary fence around the core logic. It tells the agent, you are free to rewrite this workflow to handle the complex new tasks, but you absolutely cannot violate these anchor signatures that keep the simple tasks running smoothly.
Here's where it gets really interesting.
Right.
Well, the impact on the actual code the agent was writing.
Oh, the code bloat stats are amazing.
Yeah, the researchers measured the code size of the workflows. Under the vanilla, unconstrained evolution, the agent created this massive bloated code base of over 280 lines of tangled execution logic.
Just a mess.
But when they applied the CPE anchor signatures, the code base stayed incredibly lean and efficient, hovering right around 220 lines.
By setting boundaries, CPE forced the AI to find elegant, streamlined solutions instead of just endlessly layering on defensive code. The simple task performance improved from a dismal 41.8% to 52.8%, while simultaneously achieving even stronger complex task adaptation.
Stop the structural detours. Now, moving to the second dimension, skill evolution, the backpack with the 30 skill limit. We know that when it learned number theory, it threw out geometry. How does CPE solve the physical space limit of the backpack?
Instead of a ruthless overwriting policy when the 30 skill limit is hit, CPE introduces capability-preserving consolidation.
Consolidation, right.
Before a new specialized skill is admitted into the repository, CPE scans the existing skills to see if there are semantically related tools that can be merged to release capacity.
So instead of throwing out the general geometry tool to make room for an algebra tool, it figures out a way to combine them into a single mathematical multi-tool.
Precisely. It also mathematically protects historically reusable high-utility skills from direct deletion. It forces the agent to integrate and condense its knowledge rather than just paving over it.
Which is how actual human mastery works. We don't delete basic math when we learn calculus, we integrate it.
Exactly right.
Okay, the third dimension is model evolution, the physical neural pathways. How do you stop the medical AI from rewiring its anatomy knowledge when it learns dentistry?
This relies on highly effective technique called elastic weight consolidation, or EWC.
EWC. Okay.
To understand the mechanism, imagine the AI's neural network is a massive interconnected web of pathways. CPE uses something called Fisher-style penalties to calculate exactly which of those pathways are most critical for the old anatomy domain.
So it maps out the exact route the AI uses to solve the foundational problems.
Yes. And then you can think of these Fisher-style penalties as spraying a protective, hardened coating over those specific foundational pathways.
Oh, that's a cool visual.
Right. When the agent shifts its focus and tries to learn dentistry, the system detects that protective coating. It physically forces the new knowledge to route itself through different, unused, or less important pathways in the network.
It routes the new learning along lower interference directions. It still learns the new domain, but it cordons off the previously useful representations.
It creates a physical preservation of the parameters that matter most.
And finally, we have the fourth dimension, memory evolution, the dynamic cheat sheet that was getting buried under new facts. How does CPE protect the memories from retrieval competition?
Through a mechanism called evidence-gated preservation.
Evidence-gated.
Yeah. Under the old, unconstrained evolution, every single memory was treated as equally vulnerable to being evicted or suppressed. But with CPD, memories are weighed by their historical utility.
I think of this exactly like a massive Wikipedia page.
Okay, how so?
Well, unconstrained, any passing user can rewrite or delete a section of the page based on the newest information. But with CPE, if a specific fact has been cited, verified, and successfully used 100 times in the past, the page becomes locked. It can only be edited by administrators. It builds an impenetrable vault for proven facts.
That's a perfect analogy. The memories that accumulate repeated, self-verified support over time are treated as increasingly stable. They're protected from destructive rewrites. Only the lower evidence entries, the newer, unproven memories, remain fully adaptable to the new task distributions.
And the data backs this up beautifully. In the memory experiments, the old task retention recovered from 81.6% in the unconstrained model, all the way back to 83.3% with CPE.
That's a huge recovery.
It almost entirely neutralized the memory level interference.
If we connect this to the bigger picture, what we are really talking about across all four of these dimensions is the stability-plasticity trade-off.
Okay, the trade-off.
Right. This is a fundamental tension in absolutely any learning system, whether it is biological, like a human brain, or artificial, like an LLM agent.
You need to be plastic enough to learn, but stable enough to remember.
The agent desperately needs plasticity. It needs to be flexible enough to mold itself to new data, new edge cases, and shifting environments.
Sure.
But it equally needs stability to retain its fundamental shape, its core logic, and its foundational knowledge. What the researchers at UIUC have successfully done is provide a unified mechanism to mathematically enforce this balance across every single layer of the agent's anatomy.
Which brings us to the real-world application. Why this highly technical research matters to you listening right now. Because this is not just academic theory about benchmark scores and medical data sets.
No, not at all.
The entire tech industry is aggressively moving into an era where we aren't just typing a prompt into a chat window to get a quick recipe. We are deploying autonomous agents into our daily lives and our core infrastructure.
We are entering the era of long-horizon agents. Systems that will be turned on and expected to run continuously for months or even years, constantly adapting to our needs.
And if you are relying on an autonomous agent to manage your chaotic inbox, or run the energy grid of your smart home, or automate the complex supply chain logistic for your entire business, well, you need it to be deeply, fundamentally reliable.
Absolutely.
You absolutely cannot afford for it to slowly unlearn its basic routine functions just because it encountered a bizarre new edge case today. You can't have your smart home agent spend a week figuring out how to perfectly calibrate your new solar panels, only to suddenly forget how to turn on the lights in the living room.
This raises an important question for you to consider. How much trust can you place in a system that might quietly forget how to do the most important part of its job while you aren't looking?
That's the real issue.
The trust we place in long-horizon systems requires them to actually be monotonic. We expect them to compound their competence, not quietly trade it away in the background. This research represents a massive, necessary shift.
A shift from the lab to the real world.
Exactly. It is the transition from building AI that just passes a single isolated test in a laboratory to building robust AI that can actually survive a lifetime of learning without suffering structural collapse.
It is a critical foundational step toward any kind of reliable artificial general intelligence. So, to wrap up our main takeaways from today's deep dive into the UI/UC paper, we have seen that the current dream of the unconstrained, self-evolving AI agent is deeply flawed. These agents suffer from severe capability erosion when they learn new, complex tasks. This catastrophic forgetting is not a random glitch. It is a structural consequence of destructive interference occurring across their workflows, their skill repositories, their physical neural models, and their memories.
Uncomfortable.
They fall victim to literal capability decay, paralyzing policy drift, and hyper-specialized generalization erosion.
But the cure exists. By implementing capability-preserving evolution, or CPE, we can mathematically constrain this destructive drift.
Right.
By utilizing anchor signatures to stop loaded workflows, skill consolidation to maximize repository space, parameter weighting to protect neural pathways, and evidence-gated memory to lock in proven facts, we can finally build autonomous agents that accumulate knowledge reliably over time.
It is genuinely incredible research that solves a massive problem. But, before we go, I want to leave you with one final provocative thought. Something for you to mull over that builds on everything we have unpacked today. We have spent this entire deep dive analyzing the mechanisms required to stop an AI from forgetting. But if capability-preserving evolution builds an impenetrable vault, making it incredibly hard for an AI to forget historically reliable behaviors, what happens when we want the AI to unlearn something?
Oh, that is a very complex angle. You are talking about the permanence of early behaviors.
Exactly. What if an autonomous agent learns a highly efficient but terrible bad habit early on in its deployment?
Right.
Or worse, what if it learns a subtle security vulnerability or a flawed logical shortcut, and it uses that flawed behavior successfully just enough times to trigger the evidence-gated preservation?
It's locked in.
Does this incredible preservation system inadvertently lock that bad habit in a vault? Does CPE make it mathematically impossible to erase a deeply ingrained mistake?
That's fascinating.
It is something to chew on next time you ask an autonomous agent to learn a new trick. You might just be making that trick permanent.
It perfectly highlights that every major solution in the evolution of AI inevitably introduces an entirely new set of complex challenges.
It absolutely does. Thank you for joining us for this deep dive into the hidden world of AI capability erosion. Keep questioning the evolving tech landscape around you. Keep looking for the structures beneath the surface. And maybe, just maybe, double-check that your brilliant new assistant still knows how to tie their shoes.